It seems obvious. When a solid, rigidly connected object moves through space, every piece of that object travels at the exact same speed. We can test this assumption with a simple scenario: a solid block sliding in a straight line from one location to another. If we track 3 distinct points across this block, labeled A, B, and C, we can map their journey. Because these 3 parallel dashed lines are mathematically identical in length and direction, we know the points share the exact same linear displacement. This is pure translatory motion, where the whole behaves exactly like its parts. But these rules change when we stop sliding the object and force it to spin instead. Let's shift our perspective to an object securely pinned to a central axis of rotation, continuously spinning in place. Those 3 points, A, B, and C, are no longer moving in straight lines. They now move in circles. To map this, we use the angle theta to measure rotation. Every point sweeps through that same wedge, covering the exact same angle simultaneously. This unified sweeping of angles is what we call angular displacement. Because their angular displacement is equal over time, their angular velocity, or omega, must also be identical for every point on the object. This shared angular movement is why a rotating rigid body is able to stay together as a single unit while it spins. However, while the mathematical angle is shared across the entire object, the actual physical distance traveled by each point is not. Compare point A near the axis to point C at the edge. A traces a tiny circle. C covers a much wider path. This arc length is the linear displacement. Unspooled flat, the length difference is obvious. Identical angular displacement creates unequal linear displacement. This means that parts of the same rigid object are traversing different physical distances simultaneously. A point's linear displacement is determined entirely by its distance from the axis of rotation. In rotatory motion, the parts of the object no longer move in unison with the whole, requiring a different approach to measure their speed. This leads us back to our paradox. How can a solid, rigidly connected object have multiple different speeds at once? The displacement data gives the answer. Point C on the edge travels a much longer distance than point A in the same time, forcing it to move at a much higher linear velocity. While the object's angular velocity remains constant, its linear velocity increases the further you move from the center. This provides the criteria for physics analysis. We define motion by looking at the displacement of individual points, rather than looking at the object as a single unit. If every point on an object shares the same linear displacement, the object is in pure translatory motion. If every point shares the same angular displacement, but has different linear displacements, it is pure rotatory motion. This is the rule used to deconstruct any complex physical movement.